Well, hello. And today we're going to be discussing force, and specifically we're going to be talking about Newton's first law.
Alright, what you're going to learn today, you're going to be able to identify what a force is. We're going to be able to discuss Newton's observations of objects in motion, distinguish between a balanced force and an unbalanced force, identify different forms of friction, and be introduced to inertia. Or force. What is a force? A force is any push or pull. And it has to cause a resting object to move. It can cause a resting object to move. It won't always cause it. It can accelerate a moving object by changing the object's speed or direction. So a force is anything that causes something to move, and when you apply that force, it can accelerate a moving object. So if it's already moving, it can cause it to go faster, or to slow down, or to change direction. So it's any one of those three things could happen if you apply a force to a moving object. When it comes to something that's at rest, you can apply a force to it and it may not move it at all. So, three things I really want you to get from this. If it's already moving, there's three things that can happen. One of those things, I'm trying to get my pen to pop up here. Okay, it can make the object's speed change. Changing the object's speed, meaning it can go up or it can go down. Or it can just simply change the direction. If either one of those three things happens, it goes up, it goes down, meaning the speed, or it changes direction, a force was applied. Units for force. Well, a Newton. 1 Newton, alright, 1 Newton, there is the units for force. A kilogram meter per second squared is equal to 1 Newton. It's a derived unit. Force is a vector. Why is it a vector? Because it's going to have a magnitude because of the acceleration, and the mass. They're going to have some number. The force was 500 newtons, 700 newtons, 600 newtons, 5,000 newtons, 0.2 newtons. But it's also going to have a direction because of the acceleration. The accelerations always act in some direction. So the force, you have some number, some magnitude acting in a direction. So force is indeed a vector. Other situations we need to talk about here is when we combine forces. A balanced force. Alright, this is when we use the net force. Quite often we'll say there's no net force. No net force, alright, if we say there's no net force, that means the forces are balanced, meaning however much force that you're pushing with, the object or somebody else or something is pushing back with that exact same amount of force. So the forces are balanced. And if that's true, there'd be no change in the object's motion, meaning it's not going to increase in speed, it's not going to decrease in speed, and it's not going to change direction. That's again if there's no net force or balanced. Unbalanced. Well, in this case, we would say there is now a net force. In this case, there is a net force. And one of those three things is going to happen. It's either going to A, speed up, B, slow down, or C, change direction when there's an unbalanced force. Frictions. All right. Here in a couple days, we're going to spend more time discussing friction. But for right now, I'll just let you copy these down. There's all different types of frictions that deal with force. Friction is a force, though. All right, because what is friction? If you rub your hand, or if you take a car and rub it and it goes across something that has lots of friction, it's going to slow down. Well, that was a force. It took a net force to cause that object to slow down. If your wheel is spinning and you apply a certain amount of friction to it with your hand, it's going to cause it to slow down. Alright, this takes us then to Newton's first law of motion. Newton's first law of motion says an object at rest tends to stay at rest. An object in motion tends to stay in motion with straight line constant velocity. We'll get to this bottom part here in a second here. So if I had a car, Newton's first law we're going to say this car's heading to the right. Newton's first law of motion says that once we got this object, let's say if it's sitting there, an object at rest tends to stay at rest. That car is going to sit there forever, according to Newton's first law. It will not move. Also, once we got it moving, it would continue. The second part of this tells us that if we had it going at 50 miles per hour, it would forever continue going at 50 miles per hour in a straight line. So why don't cars act that way? Well, because there's this net force that acts upon them. All right, there's this net force. Go back to our first example. Why does a car not sit in one spot for its entire life? Well, because when you get into it and start the car, there is a force that's applied to the tires which causes the car to move. That's the net force that's acting upon it. Or something else can hit it and apply a force to it and cause it to move. Why doesn't it keep moving in a straight line path? Once we get it going 50 miles per hour, why can't we just take our foot off the gas pedal and keep going at 50 miles per hour? Well, there's a net force that acts on it. Wind gives us a frictional force. All right, so the net force in this case is supplied by friction, and that is the net force that's acting upon it. So it would be going 50 miles per hour, and the wind is giving it applying a net force to it, which is decelerating. It's causing it to slow down. Why does it change direction sometimes? Why doesn't it still go in a straight line? Well, because when you turn your tires, the tires apply a force to the road and causes your car, and it also applies a force then back on your car, which causes it to change direction. Inertia, the last thing I want to discuss here today. Inertia is the tendency of an object not to accelerate. Accelerate, again, means not to change direction, it can't speed up, and it can't slow down. Well, it means inertia has this tendency to resist change to its motion. Right? What do I mean by this? For example, a hippo has lots of inertia. It does not, it's got three things here again. Once again, speed up, slow down, change direction. A hippo, it's not easy for a hippo to speed up. It's not easy for a hippo to slow down. And it sure as heck is not easy for a hippo to change direction. Whereas a piglet, if you've ever watched on TV, piglets dart all over the place. It's almost impossible to catch a piglet because they can change direction, they can speed up, and they can slow down very quickly. A tank, for example, doesn't speed up very easily, doesn't slow down very easily, does not change direction very easily. Whereas a motorcycle, they can speed up, slow down, turn, they do all types of things. What we're talking about here then is big items, things with mass, lots of mass, versus small items, things that have a little mass. Things that have lots of mass have lots of inertia. Things that have a little bit of mass have less inertia. They still have inertia, just not as much. So, for example, an alligator. How do we get away from an alligator? This is what I always come back to. Well, an alligator can run faster than we can. So, if you've got this alligator, let's give him here with his teeth, there's his legs, there's his other legs, and then his tail. Alright? And then you've got this human. Alright? Stick human, there we go, good enough. If this human just tries to run straight, the alligator will catch him and eat him, because an alligator can run faster than we can. So how do you get away from an alligator? You use your inertia, or his inertia, against him. You zigzag. Now you can't zig when he's zagging, otherwise it's chomp. But when an alligator gets moving, let's say to the left at this angle, a human who has less inertia can quickly change direction. Whereas the alligator might have to really take a rounded turn because he can't change direction nearly as quick. Well, hey, that concludes our notes today on Newton's first law. I hope you've learned a few things. Come ready tomorrow to ask some questions, and I'll see you on the flip side.